Recorded is rolling. It is Monday, December 5th. So I have a few things lined up for you guys today. Got the starter question that involves this turntable. We'll do a center mass activity. I got a Kahoot for you guys. Conceptual questions on rotational dynamics. Later this week. Tomorrow, I have a rotational inertia lab lined up for you. We'll do some review questions on Wednesday. We'll have an in-class open notes quiz on Thursday on rotational dynamics. We'll start the midterm review on Friday. So let me give you guys a visual for this right here. Got a turntable, give this thing a spin, and because there's some frictional torque, this will eventually slow to a stop. And so take that model right there. Let's tack some numbers to it. Suppose it was originally rotating at 20 radians per second. Ooh, that could be like omega, right? 20 radians per second. And say it takes 5 seconds to slow to a stop. So at what rate was it slowing down? Let's call that angular acceleration. I think the letter for that was alpha, right? Greek letter alpha, be radians per second squared. And the follow-up question is, how far did it turn? What was the angular displacement, say in radians? If you know what you're doing, go ahead. If you need another hint, you guys see a poster hanging from my ceiling that looks kind of like this? Right? This is one way to get to the answer. Or tell you what, there's actually a graph you can draw where you can answer both those questions without any equations at all. Well, any of those kinematic equations. I'll show you guys all the ways, but see if somebody gets this first. What rate is it slowing down? How far does it turn?
Oh wow,
So who can tell me the angular acceleration? Nobody got it?
Is it 4?
Yeah, -4.
-4.
Radians per second squared. Right. So one way to get it, not the only way, but here's one way. You do omega final equals omega initial plus alpha times t. Okay. So it was spinning at 20 radians per second. That goes right here. Got your 20 radians per second. Oh, it's slow to a stop. Okay, slow to a stop tells you what? Omega final is 0 radians per second. And it did this all in 5 seconds. Okay, subtract 20, divide by 5, and also the units divides over, right? So it's radians per second divided by seconds. I'm getting alpha is equal to -4 radians per second squared, right? Subtract this, then divide by 5 seconds. Okay, now you guys know the rate that it's slowing down, which could be really helpful, especially if you like using these equations to get to the answers. So the other question is, how far does it turn? Now, which variable here represents how far it's turned?
Theta.
Theta, yeah. Right there. Or if you like, it shows up here too. So take your pick, whatever's your favorite. Okay. Somebody tell me, how far has it turned in radians?
Is it 150?
Okay, less than that.
I got 50.
Got 50? Ah, yeah, I'm gonna go with what Cody got.
I forgot to
50.
put -4 in. I just put
All right. Yeah. All right,
yeah,
so here's that first kinematic formula, which is analogous to x equals v naught t plus half at squared, right? So now we're solving for the theta, right? How far does it turn? Was going 20 radians per second. Got 5 seconds. 1/2 alpha we just solved for. That's that number right there. And then 5 seconds shows up again. Don't forget to square that. Yeah, so you plug it all in, you should get 50 radians, right? And that is theta. Ooh, could you guys solve for how many revolutions that is? Let's see, 50 radians. How'd you go? Yeah, divided by 2 pi. Right. I gotta group that in. Whoops. Group that in parentheses, the 2 pi. But that is almost 8 revolutions. So it's a little bit short of 8 full turns. Right? That's what 50 radians is. Now, you could have instead used this third kinematic formula. Would have been a few more algebra steps to extract this data. Right, this one's set up to solve it, this one. But you know, let's do this. Let's take the fact that you know the answer is 50 radians. Shouldn't this zero out, give you 0 right here? Okay. But let's check that. Let's check it from knowing what the answer is. So what's going 20 radians per second? Square that. Plus 2 times -4 radians per second squared times the answer of 50 radians. Should give you 0, right? Take square root of 0 is still 0. Ah, sure it is. Look at that. Look at that. Check that. Okay. So there's a few ways to get it. Okay. Let's do one more way. All right, one more method I want to do with this. Let's do the graphical method. So here, I'll write down your givens again. You guys know omega naught is 20 radians per second. You guys know omega final is 0 radians per second. And this all happened in a time interval of 5 seconds. Okay. So what if I give you guys a pair of axes and it goes omega and radians per second as a function of time and seconds? Origin point. Okay. Can you guys draw the graph for the problem that we've been solving? That particular graph, omega versus time.
0 seconds, you get 20. So the y-intercept is 20. The x-intercept is 5.
Boom. Just like that. There you go. I like this, right? Right.
And then you just take the slope of that.
Yeah, the slope. Guys, what does the slope represent?
Acceleration.
Yeah, angular acceleration. Rise over run. Loses 20 over 5. Hey, that's -4, right? -20 over 5. Then radians per second. That's called radians per second squared. Boom. And how can you get theta from this graph? What property of the graph?
Area?
Yeah, the area, right? And if either you forgot or didn't know, or you're seeing this for the first time, you can figure it out by looking at the units. Radians per second, seconds, because I know radians per second and seconds. See, if I multiply those two, seconds cancels, I get radians, which tells you that the area under the curve, because if you multiply, right, like base times height has something to do with the area, right? Now, if it's a triangle, it's 1/2 its height. So I can call this area theta. Theta is 1/2 times the base of 5 seconds. That's a height of 20 radians per second. Let's see, half of 20 is 10 times 5, that is 50 radians. Right, seconds cancels, you get radians. There you go. Right, so there's a few different ways to do that. Right. You guys ready for your next activity? Right, so got some foam boards going around. Now the one I have for the example is like a T shape, but you guys have your own.
Are you trying to find the center of mass?
Yeah, center of mass. Yeah. So take you guys through different ways to do it. One way is, so I'll give you guys multiple choice, right? One way is the only point that your finger, it will balance on your finger. So if I turn this upside down and do it blind, if I put my finger off to the side, there's going to be a net torque, but somewhere it'll balance. All right, looks like right about here, got it. Okay, so I did the whole thing blind, so I got it upside down, but if I flip this over, type it right here. There we go. Yeah, so my finger is right on the point D, so D must be the center mass of this piece. Okay. A second way that you guys can get the center mass, I gave you guys a string with some binder clips on it. So if you take one of the binder clips and clip it anywhere on the perimeter of the foam board, okay, and you let the other binder clip act as a weight and let it hang straight down. Okay, okay, so I have to do this off screen here. Bring this over here. Okay. You guys see that green string goes right through also point B on my board, and you guys can split it, right? So that'd be the center map. Let me hold this down and then just show it in front of the camera. Right. So it'd be like that. It goes three. Right. But there's something special about this point on the perimeter. You could take any point anywhere around. It would always go through that point, through the center map. Okay. A third way you can get the center maps. What if I take this thing and I chuck it through the air? Right. And what if I attach an LED right here, an LED, and I chuck it through the air? Is that LED going to go look all spirally? I think it would. Okay. But what if I put the LED right on the center mass? What would that look like? I think it's going to make a nice smooth parabola. Yeah, and that's the only point that would happen. Okay, so this would actually spin about its own center mass and flying through the air. Okay. And center mass would actually follow like all those like projectile paths. So actually projectile physics from back in the day. All right. All right, you guys ready for some conceptual questions? I gave you guys a half page, has 20 conceptual questions on it about rotational dynamics. And so, all right, let's see. I'm gonna flip the screen over here.